G'day, in this video we're going to be looking at instantaneous velocity, average velocity, and acceleration. In this video we're going to be covering a few content points, 1.1, point 1, 2, and 4 particularly. We're still in module 1, we're still looking at inquiry question 1, we're looking at the motion of objects in a straight line, being able to describe and predict that motion. The content of this video doesn't directly address any of these content points in full, but again, we're continuing to lay a lot of foundation for how we can measure motion in order to achieve each of these content statements to their fullest. Some things that we're introducing today is the analysis of instantaneous and average velocity. You're just getting the basics. And we're also looking at broadening our understanding of velocity and acceleration a little bit more than we have already, so that we can begin to conduct these practical investigations in the coming lessons. So our learning intentions today is to be able to first distinguish between what instantaneous and average velocity are, to deepen our understanding of acceleration further, and also to be able to do some simple calculations around average velocity and acceleration as well. So first off, instantaneous versus average velocity. As soon as I started looking at this concept, my first thought when trying to deliver it to you was to go to my car, turn it on, and take two of these pictures here. My speedometer here is very good at measuring instantaneous velocity, what the current speed of an object is, and technically as well, the direction that it's going into. The average velocity is a measurement of speed as well as the direction of that object over a period of time. In the case of my car, when it says here that the average speed is 63 kilometers per hour, it doesn't mean that while my car is on, it's just traveling at 63 kilometers per hour and that's it. The average is an indication of all speeds at all times. This measurement is taking place. So at some points, the car might be stationary. At some points, I would be traveling slower than 63 kilometers an hour, but a lot of the time I'd also be traveling above this speed. Again, the average is just the mean of all of the speeds at all the times a car's been driving since it was reset. Bit of a challenge question for you to think about, something that we'll talk about in class, is that the images that I'm showing you, the speedometer and this average value here, is technically not displaying average velocity. Instead, it's displaying speed. And the question for you that I want you to be thinking about is, why is it showing speed and not showing velocity? Something to think about. Now, when we're calculating average velocity, there are a few ways that we could represent the equation to do so. Generally speaking, we display average velocity as VAV. You'll see that the AV is written in what we call subscript. It's a script that's sitting a little bit lower than the normal writing. That can be determined by doing S over T, which is our displacement divided by time. You may see some representations of the equation which include delta T, which just means change in time. You might also see representations which again include our vector pronumerals with a little arrow on the top as an accent. These representations again don't show up on your data sheet, but originally did before there was a last minute change. When we're calculating the average velocity, we want to be keeping in mind two different things. Where did the object go? In other words, how far did it go and in what direction? That's our displacement S. And how long did it take for the object to get there? That's the time. Note that this equation is not in your data sheet, but is a pretty simple equation that gets used over and over and over again, so it should be one that you get familiar with quite quickly. Keeping in mind, when calculating velocity, we are looking for pronumeral V. That's kind of what we see here, just with the little addition of AV indicating that we're working with an average velocity. Units of measurement, meters per second. It is a vector quantity, so again, direction is something that we are looking for in a final answer. Now, acceleration, we talked about a little bit in the last video. I'm going to give you a little bit more information to continue to round out our understanding and definition of what that is. Acceleration is a change in velocity. What that might mean is there's a change in speed. There could also be a change in direction as well. This direction component to acceleration and velocity is something that we're going to build on in the second inquiry question of this module. Key thing to keep in mind though, acceleration can also be instantaneous or average. We could be looking at the acceleration that's happening in the moment. We could also be looking at the acceleration that's happening over a period of time as the object travels over a set distance. Instantaneous acceleration is a reflection of what the object is doing now, how much is it speeding up, how much is it slowing down. An average measurement is looking at measuring what's happening on average during a period of time, not looking at how that acceleration may change and differ over the period of time. The two examples here have acceleration that's going forwards in this example. So the drag car is increasing in its velocity. It's building up its velocity. You would see the speedometer going up. In the example over here, we have what we call negative acceleration, or a very quick deceleration, the slowing down of a vehicle in a very, very, very short space of time. So two extreme examples of acceleration, one where the car is speeding up, one where the car is slowing down. Here we would call this positive acceleration. Here we would call this negative acceleration. That idea of positive and negative is something that we're going to build on in the coming lessons too. When we calculate acceleration, what we're looking at is first, how much did the object's velocity change? Did it go up? Did it go down? How long did it take for this change to occur? So that's the time period. Generally speaking, you'll see one of these equations representing acceleration. We might see delta V, change in velocity, over delta T, change in time. We could also show this delta V concept as V minus U. A lot of the time, if we can find the instantaneous final and initial velocities, in other words, V for final, U for initial, we can put them into our calculation because that's how we generally calculate changes in things. We take the final measurement, subtract the initial measurement. There is another way that we can show initial and final velocity. We can use subscript instead. So VF would be for the final velocity, and VI here would be the initial velocity, the starting velocity of the object as those measurements are taken. Again, you may see some representations which include the arrows at the top indicating that we are working with vector quantities. Also, this one is not in the data sheet, but again, just like when calculating for velocity, you'll find that you're using it quite frequently. It's not exactly needed within the data sheet. It is one of those fundamental equations that are used quite a lot. I have two practice questions to quickly go through as some demonstrations, one to show how to calculate average velocity, the other one to calculate acceleration. While I'm doing this, I'm going to be demonstrating a lot of the key steps that you need to do when undertaking a calculation to model what that process looks like. So in our practice questions today, we're looking at Beth, who's driving down a road which is 3 kilometers in length and heading due north. We're being asked to calculate her average velocity in kilometers per hour if it takes her 55 seconds to complete the drive. Following up with that, we're then looking at a deceleration process, a slowing down. She places her foot on the brake for 4 seconds and slows down to 40 kilometers per hour, being asked to calculate the acceleration of the car in meters per second. Before we begin, I'm just going to take some notes on some of the key things that we need to be doing when completing calculations. First thing that we always need to be looking at completing is a data column. Then once we have our data all together, making sure that we're selecting the right equation, ensuring that we have correct units of measurement before we begin to solve. We can then go about solving our equation, then substituting in, and doing a final check on our units of measurement would be good as well to make sure that we are matching the units of measurement required in the final answer. I'm going to split the question up into two parts, part A as well as part B. We'll have a look at part A first. So let's draw up a data column to begin with. So Beth drives down a road which is 3 kilometers in length, meaning that the displacement by the end, 3 kilometers. We can also put the note in that this is in the northerly direction. We also know our time. Time for this to happen is 55 seconds. And what we're being asked to determine at the end is the average velocity. This is currently unknown. Also, it's just important to add as well, we don't know if Beth's velocity was consistent or not. There's no information in the question which sort of directs us either way, which is why we're just calculating an average velocity for the entire trip. We've now done our data column, which means next we need to select an equation. Here I'm going to write that VAV or V average is equal to S over T. We then need to make sure that our units of measurement are all good. Note that we're being asked for a velocity of kilometers per hour. So we're going to need to do a bit of a conversion to go from 55 seconds to hours. The way that I'm going to do that is divide 55 by 60 twice. The first division will convert it to minutes. The second division will convert it to hours. And that number is 0.0153 hours. We've got our data using the right units of measurement. we have our equation. The next thing that we need to do is solve and substitute. Now, fortunately, our equation has already been solved for. V average is our subject. It's alone and by itself on one side, and that is our unknown that we are looking for. So we can immediately go and substitute for this question. So from here, we can take our V average and substitute in. So we're going to put in our displacement of 3 kilometers divided by our number of hours, which is 0.0153 hours. Put that into our calculator, and our answer is 196 kilometers per hour, which is obviously quite fast, which may explain why she needed to brake so suddenly. Now, this is quite a big deceleration. We can now calculate for it as well. So let's get our data down first. So within the question, we can see that the time taken for the deceleration to happen is 4 seconds. We know that v, the final velocity, is equal to 40 kilometers per hour, and that u, which we've actually just calculated, the starting velocity, is the same as v average from part A, which is 196 kilometers per hour. That means our data column is done. Next step, select an equation. What we will need to do is select our equation to calculate for acceleration. So A is equal to V minus U divided by delta T, the change in time. Now we have T, that's 4 seconds. V and U are also known. A is the only thing that we need to calculate for. That is our acceleration, which means that we don't actually have to do any solving, not required. We can just go straight into substitution. At this point too, just considering our units of measurement, I will acknowledge that we have V and U values in kilometers per hour, but we're being asked for an answer in meters per second. This means that our units don't match. You could sort of go through the calculation either way. You could either do the conversion now, or you could do the conversion at the end. Doesn't really matter. For this one, I'm going to do our conversion at the end. So I'll sub in what we've got. So that means V is 40 kilometers an hour. U is 196 kilometers an hour. Delta T is 4 seconds. And that comes to negative 39 kilometers per hour per second. Now the units are a little bit funny, and that's because we're talking about velocity in kilometers per hour. We're going to make an adjustment in a second. But what that means is, first off, that the car is slowing down at about 40 k's every second, which is, as I said before, quite fast. You'll also notice the negative value here, which indicates that there is a process where speed or velocity is reducing, not increasing. Now, to complete our conversion, we need to take this number and convert kilometers into meters. That's going to be multiply it by 1,000. But we're also going to have to convert this hours value into seconds. To do that, we'll need to divide by 60 twice. And that comes to 10.83 meters per second squared, or meters per second per second. So in other words, every second, the car is slowing down by 10.83 meters per second. So there you go, 2 calculations, one that shows calculation for average velocity, one that shows a calculation for an acceleration. Something to note as well for these final answers, because both of these are vector, they are directional. So the average speed is going to, for part A, is going to be 196 kilometers per hour north. And our final answer for part B is negative 10.83 meters per second north as well. Now, in the next video and lesson, we're going to take a lot of the ideas that we've looked at so far, start looking at how we can visually display these concepts of displacement, velocity, and acceleration. To begin with, we're going to be using a simulator to be able to show a lot of this stuff and then automatically generate these graphs so that we can look at them really closely and begin to pick them apart. We'll see you in the next video.